All right, welcome to another lecture on inferential statistics. In this, we are continuing to build on the knowledge that we've already discussed in the class, and we're going to hang out with some of these major concepts in a new way, and hopefully by approaching these ideas in all this various settings and in various approaches, it will start to become part of your everyday language. That's my hope. Let's proceed. Okay, the objective of this class is that you will demonstrate foundational understandings of statistics, that you will become confident in your understanding of them, and that you'll be prepared to master a quiz on inferential statistics. As we discussed before, the three major categories of statistical analysis, descriptive, correlation, and inferential, are what we're building upon here. And when we think of descriptive statistics, they place the findings in the context of the sample and population that we're studying. We have our four major statistics there, which I feel you solidly know as the mean, mode, median, and range. And then we have the validity and reliability of measures that we're going to discuss more in class. This is related to how we evaluate this statistical dependence that we have on various forms of health assessment measures. Correlational statistical processes help us understand the effect of predictor variables on a continuous dependent variable, and these help us demonstrate how variables move together. We use the Pearson's R test to indicate the amount of significance, and these correlational statistics are reported as a number from -1 to +1. Remember, they do not indicate any causality, but they do indicate an association between two variables. With inferential statistics, our purpose is to predict. So we are trying to predict a future outcome based on an observed sample, and we can use several forms of statistics to predict that population. We use a p-value, and a p-value also is looked at as significant when it's less than 0.05. We have a confidence interval, and the confidence interval gives us an idea of the range in which a population mean is likely to fall. And then we have an odds ratio, and this is reported where what we want there for significance is a number that's greater than 1. But the purposes of these inferential statistics is to really predict some aspect of the population. Let's look at descriptive statistics. What we have here is a frequency distribution. Notice we're using height here, and this is one that eventually approaches a normal distribution. You can see how there's a more common height right around 117 centimeters, and there's a range of answers in here, but this approaches a normal distribution. If we were able to measure everyone in the entire world, we would find a normal distribution of height. That normal distribution is foundational for any assumptions made with inferential statistics. And in this one, one of the key concepts here is that there's standard deviations around the mean. So here's the mean, which in a normal distribution is also the median. And one standard deviation away from that mean within one is 68% of the population. When we move to 2 standard deviations from that mean, we get 95% of the population. And if we were to move 3 standard deviations on either side of that mean, we would accomplish about 99% of all possible observations. So this is what one of the foundations of inferential statistics. You see the abbreviation here for mean. This is usually more of a straight line than this one, and that's the abbreviation for mean. And remember, this is the sample mean. The population mean has an abbreviation of mu, which is an N, and that mean is the most stable of all the central tendency measures, and we use this with a normal distribution. Remember the median from your application activity, it's less stable, but we use this with skewed distributions to give a more accurate view of what the mean of a very specific, or what the middle of a very specific sample was. And then the mode is least stable, and that gives us the frequency distribution of various observations. And this is especially helpful when we're dealing with a categorical variable, and we can talk about it in a frequency distribution. So next we have correlation. Here's a correlation matrix. I want you to begin to understand how to read the matrix. Obviously, income in 2010 and the income of 2010 is a perfect correlation. So going down this graph, when we have the same column as the same row, we have a 1. So really, these two images, when you look across here, are mirrors of each other. So we can just look at the positive at this one half of the graph, and it's the same as reading below this line or above it. But let's just read above it. What we see here, if we look at the highest correlation, remember, if a perfect correlation is 1, we want to see how do these two incomes correlate. When we look at the association between the two, we see, wow, this one is high, this one's high, this one's high, and this one's high. When we see the stepwise approach here, we can realize there's a high correlation between what an income is in 2011 related to its income in 2010. Likewise, 2011 and 2012, 2012 and 2013, and then 2013 and 2014. And in addition, we can see that this was the strongest predictor, which might mean that the income in 2013 was very similar to the income in 2014. But in general, we can say here that the previous year's income is highly associated with the current year's income. And so it seems like this shows a positive correlation between each of those years. So that is how you go about reading a correlation matrix. So the strongest association for income is the previous year's income, and that is the strongest association. Let's look now at inferential statistics, and it's helpful if you would get out your handout that I gave you. We can begin filling in those, or you can double check the answers you already have on that. Some of these questions that I asked, I've continued to think about. One of them are the basic assumptions needed to perform statistical tests. So when we go to inferential tests, these are founded on laws of probability, which assume a normal distribution, random sampling, and a homogeneity of the sample, which means the observations made are all similar. And then the second basic assumption is that there's standard error of the mean, and the third, let's go with that there's two forms of inference, which are hypothesis testing and parametric estimation, or parameter estimation. But when I was thinking about this question that I asked you, I was primarily thinking about the laws of probability and these assumptions that a sample is homogeneous, that it is normally distributed, and that it's random. So I just want you to start thinking about this conceptually, that all of what we're doing with inferential statistics is based on these laws of probability, but there are these other three factors that influence the type of test we choose. First of all, let's look at means testing. This, remember, is taking a sample, determining its mean, and then seeing how that sample mean varies based on either two different groups, that's an independent t-test, which means you might have a control group and an intervention group, or a paired t-test, which involves a pre and post test of one group. So if you take one group and look at it different times, that's a paired t-test, and we can look at the means there of an effect, or we can do the independent t-test with two different groups. Another form of means testing is the ANOVA, and we use an F ratio statistics there to study the variation between groups. And although I talked about this being able to be used in two or more groups in a previous slide, which is true, I noticed in your textbook they talk about it as being in three or more groups, which is also true. I guess if you have two groups, you tend to just use the t-test, but once you get that third group, you can then look at the ANOVA and the variation between three or more groups. So here's our question posed on your handout. Once again, t-test compares two means and ANOVA compares three or more means. So the outcomes are reported with a significance in both cases, and that significance level is a p-value. Remember, it's the researcher that selects that level of significance, and that is the level of significance that's needed to reject the null hypothesis. Now, to the untrained ear, that is one of those gobbledygook kind of sentences. Remember, the null hypothesis, what that essentially means is that there is no difference between the two observations. So this usually means there's no difference between the regular population and the population that's been exposed to an intervention. So, but the researcher chooses that level of significance. I want you to know that that is not something that is calculated, it's something that's selected. Let's talk about standard deviation. With an average grade of 92 in a research course and a standard deviation of 2 points, what would it mean, the likelihood, what is the likelihood of a student scoring between a 90 and a 94? So you think about this 92, 90 is 2 less, so that's 1 standard deviation less and 1 standard deviation more than the mean. So think about that for a minute. And we'll scroll right back here and you could see, so if this is 90, this would be 88, and or if this is 92, this would be 90 and this would be 94. So it's 68% likely is how we would interpret that a student would score between those two. When we go to 88 and 96, you can see we're now 2 standard deviations away from the mean in both directions. So in this case, there's a 95% likelihood that a single student would be scoring in this range. And then when we go to 3, we know there's a 99% likelihood that a student is scoring between an 86 and a 98. And so when we look at standard deviation, it can tell us the likelihood of any individual in the sample falling within that range. Let's talk about errors of these measurements. Now, these errors are called type 1 and type 2 errors. Remember our null hypothesis? Well, in this picture, the null hypothesis is that there's no pregnancy. A type 1 error, also called an alpha, is in a case where this physician here is telling this elderly man that he's pregnant. So this is a type 1 error where the person, well, we'll talk about this some more, but this is a type 1 error. A type 2 error, in this case, the physician is telling the patient that appears to be pregnant that they're not pregnant. So these are the 2 types of errors. This one is called an alpha and this one is called a beta. Let's look at your handout again. The researcher thinks that the null hypothesis is blank in a type 1 error, but the truth is the null hypothesis is blank. Think back to that picture, the very first picture. The null hypothesis, remember, is no pregnancy. So in that case, they think that the null hypothesis is false, but the truth is the null hypothesis is true. Let's see if I did that right. Yes, I did. Amazing. Now let's think about that picture again. The researcher thinks in the second case, the researcher thinks the null hypothesis is true, but in the type 2 error, but the truth is that the null hypothesis is false. So I hope that those pictures can help you as you think about what a type 1 and type 2 error is. I myself have a lot of difficulty remembering this, but that picture has helped me to sort through the type 1 and type 2 error. And I want to also let you know that these are called alpha. A type 1 error is called an alpha error, and a type 2 error is called a beta error. I hope that helps you out. Now remember, there's two kinds of significance, and this is where even statistical studies are basically interpretive. So this is where a quantitative study is considered interpretive, just like a qualitative study, because a researcher evaluates a study for two types of significance. These are clinical significance and statistical significance. So having one doesn't necessarily mean that you have the other. So always be thinking as you interpret research, is it meaningful or not clinically? And the researcher, the author of the report, has to make that case and convince us. So we have that one part, which is statistical significance. Now let's talk about confidence intervals. A 95% confidence interval defines a range of values that you can be 95% certain contains the population mean. This is really different from a range, and I hope that this picture really can show the distinction of that. Notice when we have a small sample, we have a very large confidence interval where the mean falls, because really we don't have a large enough sample to know with what percent of confidence that the true population mean is found between. As that sample size grows, our confidence interval gets smaller because we can become more confident that the sample mean, the true mean, is found in this range. And then with a very large sample, notice the confidence interval becomes even smaller as we become increasingly confident that the population mean falls in that range. So that is how you interpret a confidence interval. Let's look at an odds ratio. The odds ratio shows the strength of an association. So it's the ratio that the odds of A in the presence of B and the odds of A in the absence of B would be determined. So two events are independent if and only if the odds ratio equals 1. So notice this is very different from our correlation, where we were trying to get to 1. In this case, a 1 would mean that they are totally independent. So be thinking about that, how this is very different from our lining up with the line in a correlation. So the odds of one event are the same in either the presence or absence of the other event would be the 1. But if the odds ratio is greater than 1, then A and B are associated. They're now correlated when it's over 1. In that sense, compared to the absence of B, the presence of B raises the odds of A, and then to give it the other way, the presence of A raises the odds of B. So this can be either in either direction, but what we're looking for is an odds ratio that's greater than 1. Remember in your application activity, I think it was like a 1.65 I think it was for men graduating from high school, And so that meant there were more men graduating in that level of education. But if the odds ratio is less than 1, then A and B are negatively correlated, and the presence of one event reduces the odds of the other event. So be thinking about that odds ratio and the strength of the association surrounding the value of 1 as you interpret that odds ratio. Statistical significance is reported with inferential statistics as a p-value. So let's look at this. How do you interpret a p-value of 0.046? Well, if a researcher had selected a significance level of 0.05, then this is now a significant p-value. However, if they'd chosen a p-value of 0.01, this would be considered not significant. So remember, this is the likelihood that 1 out of 100 of the observations were actually found by chance. Here we have 4.6 of the observations were actually found by chance. So all 3 of these values could be considered significant depending on the level of significance that the researcher selects. Generally, a significance of 0.01 is chosen for a group that has maybe a smaller sample, because with a smaller sample, you might want to be more strict about what you consider significant findings. And with a larger sample, the larger your sample size, you might be able to be more lenient with that. So those are just some of the choices that researchers take. Now, how would you interpret this confidence interval of 3.02 to 6.4? We don't really have any context. We don't know what kind of number. There's no label on this. But what this means is the true population mean falls somewhere between 3.02 to 6.4 if this was, for say, a 95% confidence interval. So this is looking at just the opposite of here. Here we're saying our true mean falls somewhere in this range. Don't view it and misinterpret it as a range that contains 95% of all the values. That's not what it's looking at. It's asking, where is the true mean of the population? That's what the confidence interval is. So this is not the range. This is a range where the true mean or the central tendency is within a sample. And then if we have an odds ratio of 1.64, we can say that there is an association between whatever 2 variables they are, that it's moving in a positive direction. So these are 2 variables that are positively associated. There's usually a p-value reported along with this odds ratio that will let you know if this is a significant relationship or not. So those are how we interpret those values. Let's look at the levels of measurement needed to select a statistical test. I provided on here a link with a very detailed table of these. I am trying to simplify this content for you and just give you a few of these values. Remember, I've focused a lot on the chi-square being categorical. That could be nominal or ordinal data. Then the t-test, ANOVA, and correlation, the dependent variable, all needs to be in this interval or ratio area. So that is different from categorical data. Instead, it's in this ratio. A mean, of course, we can't calculate a mean on categorical data. It needs to be interval or ratio, whereas a frequency, we can take nominal and categorical data and report them as frequencies. So just wanted to sensitize you to that again, about those types of data. Let's look at this index of risk, this odds ratio. An odds ratio describes the blank for a health event. The confidence interval provides a blank in which the true value of the event is found. So the confidence interval provides the range in which the true value of the event is found. Remember, that's a true mean. whereas the odds ratio describes the risk for a health event. Also consider using the term likelihood for a health event. Let's look now at correlational coefficients. The difference between a regression and a correlation is the blank of measurement and the blank of the sample. The dependent variable goes on which line in a graph displaying a correlation. These are questions from your handout. The difference between a regression and a correlation is the level of measurement and the characteristics of the sample. So remember, with a regression, we want to have all those assumptions where there's a normal distribution of data. We want to use the interval level data and have all the assumptions of, for a regression, of the inferential statistic. Whereas in a correlation, we have, we can use a nominal level of data, basically at the group level, but we're just looking at an association there. We're not predicting like we do in a regression. So when you have the independent variable, we need that to go on the vertical line. The dependent variable goes on the horizontal line when we're displaying a correlation. So that dependent variable needs to be on the horizontal line, and that dependent variable is generally at the interval level, whereas the independent variable can be at a nominal level when we're displaying a correlation. Finally, I think this is finally, we have the chi-square. I think you nicely understood that this is essentially proportions that are used to demonstrate the independence or homogeneity of a specific categorical variables. This is how that's called the chi-square, is the test statistic, and is reported with a p-value to indicate if that independence or homogeneity is significant. So the difference between a parametric test and a non-parametric test, once again, is the level of measurement, and remember the importance of the distribution of the sample, which is the basis of inferential statistic, needs to be evident. So this series of slides has prepared you to do fabulously on Quiz 5. Thank you for continuing our conversation of inferential statistics. I really believe in repetition and hope that as you have watched the 5 previous slide sets, you've worked through the handout, you've done the application activities, and now you've worked through this slide set. I hope that the language of inferential statistics and the isolated tests that I've selected for us to focus on in this course will help you feel extremely confident in these concepts as you read and understand research. Thanks for spending this time to learn more on these important topics.